What is the world we live in literally made of? The most convincing scientific theory to date is the string theory, which states that the universe consists of one-dimensional strings and their vibrations. These string theory have evolved into superstring theory, M theory, and F theory. This means that the vibrating strings become the basic element that brings about the change of all things. Today, I will tell you a brief introduction of string theory and its meaning to understanding of our universe. Let's start. The length of this string is very small, about 10 to minus 33 centimeter. That is the Planck length. But unlike point particles described in conventional quantum mechanics or quantum field theory, they can be viewed as waves and particles in a finite size. So, how can these vibrations of string explain all the elementary particles in the universe, including us, and the interaction between them? Let's say you play the violin. A violin has 4 strings, and the vibrations of these strings produce sounds and tones of various frequencies. The basic principles of this vibration of string is the condition to become a standing wave. That is the basic principle of wave generation, that the length of the string must be an integer multiple of the half wavelength of the wave. String theory's string also satisfies the condition of a standing wave in a spatial region smaller than the Planck length. Also, just as the vibration mode of a violin string changes its tone, if the vibration mode of the string changes, elementary particles have different masses and force charges. String theory is a strong candidate for the theory of everything, TOE, which aims to harmoniously unify the gravitational force described by the general theory of relativity and quantum mechanics that describe the microscopic world. There is also loop quantum gravity theory as another unified quantum gravity theory, but it is an extension of the general theory of relativity that sees gravity as a space-time rather than a force. This is another theory. However, both theories are based on quantum field theory, which describes forces and matter as excitations of field. The greatest achievements of string theory is that it predicts the gravitational force, a gauge boson particles of spin 2, from the vibration of a closed annular ring. This suggests that the general theory of relativity and quantum mechanics can be fully integrated from string theory to explain all the basic particles in the universe, suggesting that it can be a grand unified theory. Let's take a moment to look at elementary particles in the standard model. According to today's quantum mechanics, more specifically, gauge theory with a symmetric group, there are 17 elementary particles in the universe. There are 4 types of particles, including W+, W-, and G0 particles, which mediate weak forces, photons, which mediate electromagnetic force, and gluons, which mediate strong force. These are all particles with a spin of 1, and in the beginning of the universe, they did not have mass like photons and existed as the same force. It is the explanation, according to the gauge theory of the standard model, that it has evolved from spontaneous symmetry breaking, known as the Higgs mechanism, which gives mass to the gauge bosons that mediate this weak and strong force and interact with the Higgs field as today. So vacuum is full of energy with the Higgs field, and its emptiness is matter. On the other hand, fermions, the basic particles that make up matter, are composed of first, second, and third generations of quarks and leptons. It consists of up, down, charm, strange, top and bottom quarks and electrons, neutrinos, etc. As the first, second, and third generations go on, the fermion particles are known to be in a state where the vibration frequency of the string is increased, that is, its energy is higher. Early string theory could only explain gauge bosons, so supersymmetry was introduced to explain the other fermions that make a matter. So it was extended to superstring theory, and it was also possible to solve the problem of the existence of tachyons moving faster than light. Supersymmetry is a story that there is a twin fermion particles for every boson particle that mediates a force, and conversely, a corresponding boson particle exists for fermion particles that make a matter. So, how do these strings vibrate? How is the tension of the string given? Let's look at these fundamental questions. To know the vibration pattern of the string, it is necessary to know the dimension of the space in which these strings vibrate. There is a Calabr-Yau space as a mathematical space to describe it. In the 10-dimensional world claimed by string theory, why do we perceive only 4 dimensions, including 3-dimensional space and 1-dimensional time, explaining that the remaining 6-dimensional space is hidden and crumpled in a very small area of a 3-dimensional space? In 1984, Philip Candelas, Gary Horowitz, and Andrew Strominger and Edward Witten found a solution to a set of 6-dimensional figures that satisfied the string theory equation, which called as the Calabr-Yau space, and this was named after a mathematician who had been studying it before. One form of Calabr-Yau space is like a picture. It is one of tens of thousands of possible 6-dimensional space forms. If you can find one form that describes our universe out of tens of thousands of possible Calabr-Yau space, then you have a mathematically perfect solution. In other words, in the 3-dimensional space we live in, countless Calabr-Yau space already exist microscopically. The vibration mode of a string can be divided into closed string and open string. Gravity can be viewed as the closed string, and the remaining forces and particles can be viewed as the vibration of an open string. There are 5 types of string theories which have duality with each other. So they were later integrated into M-theory, assuming 11-dimensional space-time by Edward Witten. F-theory assumes 12-dimensional space-time, and bosonic string theory, which assumes 26-dimensional space-time without introducing supersymmetry, can also be considered as a subclass. The tension in the string is very large, known as the Planck tension, equivalent to about 10 to 39 ton. To have such a great tension, the length of string must be very short, and a tremendous amount of energy is required for the string to vibrate. This is because the energy of the string increases as the vibration frequency and tension increases. Therefore, the basic strings that make up the microworld already have a very large energy, and if this energy can be used by mankind, the energy problem on Earth can be perfectly solved. In this way, string theory is talking about the fact that everything is connected through an 11-dimensional space that we cannot perceive. In other words, the atoms that make up our body, if you look closely, protons, neutrons, and electrons, and if you look more closely, up quarks and down quarks, can all be seen as a vibration of strings and are connected to each other through tiny extra 6 dimensions that we cannot see. It indicates that the information and energy can be exchanged with others by these tiny unseen dimensions. So far, we have highlighted the strengths of string theory and its potential as a grand unified theory. However, there is a problem with the string theory. Cosmic horizon problem, cosmology described after the Planck time, 10 to minus 43 seconds from the Big Bang, is from the fact that the cosmic background radiation is the same anywhere in the universe with an error of 0.001% that we can observe. This leads to the problem of the horizon, which means that light that starts at one point at the same time as Big Bang happens can never reach a opposite point within a given time. To solve this problem, the inflationary cosmological model emerged, which states that our universe expands faster than the speed of light between 10 to minus 34 seconds from the Planck time. String theory relies mostly on perturbation theory to analyze the high temperature, high pressure, and high density states of early universe, so it has limitations and is still at rudimentary level. In my opinion, this inflationary cosmological model is wrong, and strings can move through another hidden dimensions to exchange its energy that might give cosmic background radiation almost uniform. Also, since the small radius, large radius duality of string theory is related to the minimum size of the universe, it is a matter to verify whether actual observation is possible. In terms of dimensions, it is also questionable why the dimensions that exist within the same Planck length in an early universe continue to expand only with 3 dimensions. In addition, it will be an important task to find out whether the Calabria space that properly describes our universe exists, and if so, what kind of form it is, and to find the evolution process of this Calabria space. Also, what the string is made of, and where their initial vibration energy comes from is also task to be solved. In addition, if supersymmetry is implemented, why we could not yet experimentally detect supersymmetric particles in the Saturn's LHC, which can produce a collision energy of 13 tera-electron-volts. In conclusion, string theory, superstring theory, and M theory are mathematically beautiful, but they are not yet theories of everything that can predictably explain the real physical world, and they are theories with many weaknesses to overcome. The TNS duality problem for the 5-string theories not covered today, black hole radiation theory, holographic universe, multiverse, and simulated cosmology is another fascinating topic regarding string theory. Finally, we can understand there are hidden dimensions in our space-time which we cannot perceive. However, we might transmit some information and energy by controlling vibration modes of strings someday in the near future, and everything is already in us.